Hello and welcome. Today's topic is you're using a heterogeneous multicore SoC for your next design. What's next? My name's Jeff Hancock. I'm a senior product manager here at Siemens Embedded. And today we're going to talk about all of the options you have when you're looking to use a heterogeneous multi-core SoC. So first off, what is a heterogeneous multi-core SoC? So if we take a look at some things here, so what is it? So from the hardware's perspective, it's really just a combination of different types of cores within a single system on a chip or SoC. So those could be application cores, they could be real-time cores, heck, those could be DSPs or even soft cores within an FPGA fabric. And so from that, what can you do to build upon that? So from a software perspective, layering on top of that, you start to open up a lot more different possible combinations out there. You could have a mix of a general purpose operating system like a Linux or a real-time embedded operating system. Heck, you could even put bare metal out there. Or you can even run something like a hypervisor in these things. So you can start to see the complexity start to build upon all of these new additional cores that we have. And we haven't even talked about how do you sequence all the boot, or once the systems are boot, how do you share workload between all of these different parameters? You can start to imagine now that we have all these different compute powers, the world has just gotten really complex out there. And so just in general, multi-core, right? I mean, it could be, as I said, like that heterogeneous type where you have a mix of different things. And so I'll just from now on call that heterogeneous multi-core, where all the different core groups, I'm going to say, are different. You could still also have a homogeneous multi-core where all the cores are identical. In some cases, that's maybe a group of things on a single SoC. So for example, these application cores that we see, you could have a group of them that are all homogeneous. So maybe you have a quad Cortex A53, for example, and there that are all homogeneous out there. But then you can also have maybe a hybrid where uh, there are kind of all identical cores, but they have a little bit of differences over there. So um, different power and other specialized cores that could be out there as well. So that's kind of just as we're level setting the definitions from a multi-core hardware standpoint. In real life, what's an example of a heterogeneous multi-core? So in this case, I selected the NXP S32G, and you can see on here, it's got three Cortex M7s on there. It's got quad A53s in there as well. There's a lot of different other things that come into play when we talk about some of the memory and systems and security engines and things along those lines out there. But here's just one of many different examples where you could see out there as well. So with all this, it does bring some new challenges to leverage all of this awesome compute power we have, right? And so what we've seen is some people are using these new compute systems to consolidate systems and system functions all onto a single SoC. So maybe they had different boards out there in the past, and now from a cost standpoint, they're trying to leverage and consolidate out there as well. With this, now with application cores and real-time cores, and in some cases, in some realms, they actually call them safety islands out there. You can now start to consolidate systems that are not just of the same criticality, but of a mixed criticality. So in this case, I'm talking about something like a mixed safety criticality, where maybe you have some functional safety functionality running on the real-time cores, but more of a general purpose operating system or non-safety on the application cores out there. And so really being able to leverage that opens up a whole lot more challenges, but also opportunities out there. And then when you start to sprinkle in some of the safety and to some extent security in there as well, is making sure like there's proper isolation between the different domains, and but you can still also establish a safe and secure communication between these different domains out there as well. Some additional challenges, right? So how do I efficiently utilize all the different compute resources on the system out there? Already talked a little bit about the separation. So if I do require any separation, how do I make sure that that separation is honored? And then finally, resource sharing. There's still some things that are going to have to share resources be it maybe memory, peripherals, and other things out there as well. And since this is embedded, right, other factors that we need to take into account. So do I have a hard real-time requirement? If I miss an event, does something bad happen, for example? Do I have a soft real-time where, you know what, I'm 95% of the time, I, you know, maybe, needs to be on time but I do have a little bit of balance there. Or, I don't really have any real time over there as well. And so those considerations help figuring out where and what type of operating environment we need to have in there. And then other considerations beyond that, right? Memory, how much memory do I have on here? CPU resources. So for all of these different areas, uh, you know, do I have, can I use a certain operating system in there in those for that cluster of areas? Boot time, maybe I have a hard boot time requirement as well. And so there's things that I need to understand. So it goes beyond just thinking about the hardware, but then also your traditional kind of embedded things, both from a real-time perspective, but also constraints perspective, be it memory or CPU resources. And that'll help guide you to either a general purpose operating system like Linux or a real-time embedded operating system, or a combination of both, because we do have these heterogeneous environments out here. And then finally, with all that, uh, you know, do you need to, can you leverage something like an SMP across some of these homogeneous cores that are in this environment? So these applications, like those quad A53 cores, for example, can you leverage an AMP, an asynchrometric multiprocessing out there? Can you get by with something like an unsupervised multiprocessing that doesn't really require any separation or anything like that? Or do you need to leverage some separation, but you can leverage just the hardware separations that are out there to maybe separate the different peripherals and memory and cores out on the chip? Or do you really need the capability, of a supervised multiprocessing model with virtualization capabilities out there? So think of that as something like a hypervisor capability. So as you can imagine, the world has gotten a whole lot more complicated, in things that we have to figure all these things out. So with that, I'm here to provide some guidance for you for all of these different challenges that you may run into. So first off, we'll talk about supervised versus kind of like unsupervised out there. So hypervisor, for example. So a hypervisor is a really great way to take advantage of multicores out there. It provides the ability to have different types of software environments running on top of it as what I'm going to call guest operating systems. So you can actually run multiple operating systems on here. It does enable supervision of those to have CPU access, peripheral access, interprocessor communications, as well as isolation. The hypervisor can take care of the boot sequence and also manage shared peripheral accesses out there. The nice other thing is if for some reason, if one of the guests happen to crash, it's not going to affect the other workloads on any of the other cores out there. And really, when we're talking about hypervisors, in this case, I'm talking about a type 1 hypervisor that's really, designed for true embedded systems out here as well. So some of the pros here is it does give you a lot of flexibility and efficient resource sharing out there. It does provide strong intercore separation. It does, and it enables you to also virtualize different devices out there and the ability to share them. It also gives the ability to assign ownership over peripherals and up to maybe specific cores out there as well. Some of the downsides of a hypervisor is there is some extra code over there. Now, in a lot of cases, it's not a lot, but there is an additional layer between the actual processor cores and the OS or guest that you're running over there. So with that, just by nature, there is going to be a little bit extra code over there. Technically, there's a little bit of extra overhead over here. Reality is that most embedded hypervisors these days, that execution time is minimal, but it's still an extra layer you have to go through. For the most part, they really do only work on homogeneous multicores out there. So this is getting back to that definition. So having all the cores identical. Now, I know there are some exceptions to that, but for the majority, they do run only or designed really for homogeneous type cores out there. To be efficient and everything like that does require hardware virtualization enablement in the processor itself. So with that, there is a little bit more complexity out there. And then when we're talking about complexity, this is where you start to get into thinking about, okay, do I have a pass-through that goes directly to that peripheral, or do I have a virtual driver, so a virtual UART or other things that I have to go through? What about sharing? All those other things. So there is a layer of complexity that can come into play with a hypervisor. Another option that we can talk about for multi-core here is something I'm going to label as multi-core framework. So what this really is it's enabled for an AMP software architecture. So it's really designed specifically to support multi-core applications. Its key functionality here is really twofold. It's to enable the product lifecycle, so the boot up and take down of the system or the individual environments that it's booting up, as well as once these are up, then handling the interprocessor communication or the IPC or the communication between the different environments here. So what's nice about this is it runs directly on the CPUs itself. So there's much less overhead over here, and also can be run with basic systems, including you could have this as a part of a bare metal type applications over there as well. So some pros for this is if you have a bunch of different types of environments over there, real time, not real time, bare metal, it's all ready to go there. Easy to migrate legacy software over there as well to be able to pull that in. It does have a flexible it gives you the flexibility when you're talking about different designs. I talked about the nice provisioning for boot sequences, both taking up and taking down. as well as the communication between theirs. It is really designed for these heterogeneous type environments, so it's, memory footprint is minimal, as well as its execution time and overhead. Really, it's almost, think of it as like an extra library, so to speak, that you can work into your applications or your operating environments over there. The beauty of this is there isn't that extra layer here as well, so it's directly onto the cores. So that being said, it does work out of the box with heterogeneous or different cores over there as well. And as I said, it doesn't have a requirement for an underlying OS or authos and can be run with bare metal. So some of the cons on here, though, is by nature there is no resource built-in isolation and sharing out there. So the concept of any virtualization or anything like that, that's not in this, right? The concept of having guest OSs, that's not in here as well. They're actually running directly on there. So resource sharing, you do need to think a little bit more about how that's going to happen. That being said, shared memory and other things like that isn't a problem there. And then there's also like new components for this communication and lifecycle management that need to be worked into an existing workflow over there as well. Now, that being said, there are things with hardware that we can leverage and address some of the isolation that are out there as well. So some examples of some multi-core frameworks out there. So there is a project, an open source project called OpenAMP that really is driving this multi-core framework capability. It provides that lifecycle management using remote proc facilities to control and manage the boot order and the takedown. And then also it uses standard RP message for some of that interprocessor communication. Now, some commercial offerings for that. We have the Nucleus Multicore Framework that leverages the OpenAMP capabilities, as well as then there's a functional safety version of that as well for some of these environments where you may want to have a mixed safety criticality capability. And so there are some additional things that have been added to help with some of that isolation and making sure safe world and non-safe world can play together. So with that, right, and making that choice from a management system, I'm going to call it over here. There's different options that you have. You can run a hypervisor out there. You can run a multi-core framework, and heck, you can actually maybe even mix the two out there as well. You could have a hypervisor running on what I'm going to call the homogeneous cluster within a heterogeneous SoC. Talking with the multi-core framework, talking to that cluster, plus maybe some real-time cores that are out there as well. So a lot of different factors and decisions that you can think about when it comes to that. And with that, you can, as we start to expand even more and start to think about all of these possible options, then we can add the capability of functional safety into this as well. And so now the concept of mixed safety criticality out there. So what would something like that look like? So we could take a look at the new Escalade out there as well, and we take a look at the dash over here, right? And if we take a look at the dash, there's a lot of things here, right? And there's probably a good chance that there's a hypervisor or some other multiple OSs are running in the background, right? And some of these things do have a functional safety component over there. So think about this, as you put the car in reverse, there's a backup camera that then comes up, right? And that actually has a functional safety. If you're backing up, the camera goes out, and something goes behind there and you can't see it, that's a safety issue. And so things like reverse backup cameras do have functional safety awareness over here. So now on this cluster here, you have the capability of running on a single SoC multiple operating systems that are both running in a And non-safe partitions, think about your radio. Yeah, it's an annoyance that your radio goes out, but it doesn't really cause any harm, um, other than you're really disappointed that the station you listen to went out. Versus a functional safety, something like a backup camera, where something could happen if that went out. So having on a single system here, both functional safety and non-functional safety, all on the same piece of hardware, in this case, a single SoC, are starting to become more and more apparent. You could think about this in a medical environment with like a patient monitoring type system, industrial with some type of human interaction with some machinery. There's a whole lot of different possibilities that you would think of that in the past you may have different um, boards handling the different functionality. And now from a cost and space standpoint, you can now combine those all into one over here. So real quickly, I'll go into just some components that make up a mixed safety criticality system. So obviously you're going to need some type of critical software or certified RTOS out there. You'll have different, you may have a less critical software or functional safety. So those are the different domains. You're still going to have to communicate back and forth between those environments, right? So the camera comes in, but then it gets put onto something else, right? Or there's some other communication that maybe goes through a gateway for in-vehicle gateway. It's talking, maybe it's doing some firmware updates to systems that are in the vehicle that are functional safety. So that part has to be functional safety, but the connecting up to the outside world, to a 5G tower, that maybe doesn't have to be, right? So be able to pass back and forth. Booting, right? Do I have a secure or safe boot requirement? More than likely, yes, if I have functional safety over there. Obviously, we have to worry about the isolation, but not only from a hardware standpoint, but from a software standpoint. And then also there's the whole hardware and verification monitoring side of things. There's error handling and fault and common cause type stuff. And then there's resource management. All of these things come into play to really make up a mixed criticality system. And when we also talk about functional safety concepts, then we're talking about the different faults that are on there, be it systematic, random, things along those lines. As I was talking about, a lot of these things can be handled with hardware, but then there's also software that needs to also have that design from a functional safety standpoint. So that safe boot, be able to ensure isolation out there, as well as having these components that are safety certified over there. Types of isolation, temporal, spatial, thinking also about system-wide out there, and really be able to leverage these type of things. So just, be able to have either dedicated cores, the temporal, or be able to leverage some hardware protection units, which is more spatial type there as well. When we talk about communications between the two, this is where kind of like the software comes into play. So being able to have the capabilities of being able to protect from a software standpoint the channel or channels that are communicating between the safe domain and non-safe domain. So think about this, the non-safe world, something's going crazy and it starts to go crazy and there's a ton of interrupts over here, right? Well, all that interrupt flooding needs to make sure that it doesn't affect the safe side over there. So there needs to be a way to mitigate interrupt flooding. And also then there's other things like with buffer validation and everything like that. So you can ensure that that communication between that safe world and non-safe world is protected over there. And so here's an example of a mixed safety criticality solution. So you can think about these application cores. So Cortex A53s, you could be running a non-safe world type thing. So you could have just regular Linux, you could have a regular RTOS, you could have bare metal over there. You could run a hypervisor in there as well that maybe have all these different guest operating systems out there. And then on the safe side, you could run something like a functional safety RTOS out there. Or heck, maybe if this is automotive, you could run something like an AutoSAR. You could run even bare metal over there as well, right? And then so you'll have the hardware separation, between both temporal and spatial out there between the different cores, as well as some of the hardware separation capabilities with the peripherals and memory and other things out there as well. But you're going to need something to bridge that gap, right? And that's where something like a multi-core framework that has been certified can come into play there and be able to help you bridge that gap. And that's where it helps with, prevent from things like the interrupt flooding and also the buffer validation and things along those lines. So with all that, here at Siemens Embedded, we do have a comprehensive solution for these really complex multi-core offering or projects out there. We have our SoCl suite of Linux distributions with our SoCl Flex OS, which is a Yocto-based distribution, our Omni OS, which is a Debian-based solution over there. We have our tried and true Linux real-time embedded operating system, as well as its functional safety version of that as well. So if you do have functional safety needs for ISO 26262, IEC 61508, IEC 62304, or DO 178, Nuclear Safety Cert can help you out there. Hypervisors, we've talked about hypervisors here. So we do have our Nucleus hypervisor that can leverage the use of these multi-cores out there. And then, talking about multi-core frameworks, we have our Nucleus multi-core framework as well as its certified version there as well. So with that certified version, we can help enable things like that mixed safety criticality that I just talked about and help with that isolation from a software standpoint, interrupt flooding, things along those lines. What we didn't talk about here was also our IoT framework. So if you do have devices, multi-core devices that also need to have cloud connectivity, we do have that with our IoT framework that can connect up to AWS, MindSphere, Azure, all of the popular cloud vendors out there. With all this, you still need a high quality development suite for all that, and that's where our Code Sorcery Code Bench tools come into play. And then finally, when you really want to tweak and optimize your systems, we have our Sorcery analyzing tools that can really get you there. So between that, all of our services capabilities and over 25 years of embedded experience, we have you covered here at Siemens Embedded. So with that, I'd like to thank you, and I hope you have a great rest of your show. Thanks.